Good evening to everyone. Now the topic I'm going to present today is development of texture of suture materials using carbohydrate based polymers. Now a suture is any string of material, either natural or synthetic, that is used to litigate blood vessels or approximate tissues in order to achieve proper wound healing. Sutures were first introduced by the forefathers of medicine nearly 4000 years ago, when they used strips of linen, tendons, and even horsetail to close common wounds. Today, sutures stand out as the most widely used medical device, with employment in over 12,000 million procedures per year and a huge global market exceeding $1.3 billion annually. Indeed, surgical sutures are the gold standard for treating a diverse scope of wounds, including surgical incisions, severed blood vessels, and any form of traumatized tissue such as tendons, nerves, and muscles. The successful outcome of these procedures relies heavily on the behavior of the suture material within the biological milieu, which in turn depends on the intrinsic properties of the starting material and its proper formulation into a suitable suture material. Hence, sutures have a startling and unparalleled power to directly influence the health of a major portion of the world's population. Now, the suture materials are normally classified as absorbable or non-absorbable and as a natural or synthetic material. Since non-absorbable sutures must be removed through a second operational procedure that is not only costly but also painful for the patient, absorbable sutures are generally the preferred material. The only natural degradable suture currently on the market is also one of the oldest suture materials, namely catgut. Several years after its introduction, catgut sutures were undeniably linked to the hypersensitivity reactions and abnormally high rates of infection that have caused most surgeons to reject and condemn the use of catgut sutures. Consequently, when synthetic absorbable polymers such as polyglycolic acid were discovered in the 1970s, they overtook the suture market with unprecedented common success. These synthetic polymers, however, induce significant inflammation upon implantation, which is far from ideal. Furthermore, the degradation products of synthetic sutures have been shown to cause local pH shifts that leads to more pronounced inflammation and impedes the wound healing process. Irregular degradation profiles are another troubling attribute of synthetic absorbable sutures, which are known to rapidly lose their tensile strength under certain set conditions, such as areas with high moisture content, that is, for example, blood vessels, or an alkaline nature, that is urinary tract and bile ducts. Moreover, several synthetic sutures are notorious for their poor handling properties and low pliability, which places excessive pressure on the wound edges and ultimately leads to pressure necrosis. And wound dehiscence, which is in fact the most common suture related complication. A comprehensive list of the advantages and disadvantages have been cited. Given the important role of sutures in ensuring a successful surgical outcome and their ample use in surgery, one would expect these materials to have been refined and perfected over the many years and that they have been in use. Yet the ideal suture material remains a much sought after target and future dream of scientists and surgeons alike. In recent years, several authors have suggested that the demands of modern surgery drastically exceed the abilities of available synthetic polymer sutures. Hence, a new trend has emerged where scientists are looking towards natural polymers which hold several promising properties such as supreme biocompatibility and high tensile strength with a balanced measure of elasticity to develop novel suture materials with improved safety and efficacy. The potential of natural polymers to produce first-rate suture materials was first studied by Zhukovsky, who stated that the only way to advance the field of surgical sutures is to develop new strong and elastic fibers made of biocompatible absorbable natural polymers such as the polysialoalkanates, collagen, chitin and alginate. Another strong driving force behind the use of natural polymers as surgical suture materials is a new inclination towards development of bioactive sutures with multiple functionalities. Since sutures are already in use in most surgical procedures, it is only logical that further progress in this field should entail the addition of bioactive molecules to the suture material that can be released shortly to the site of injury. This can result in high local concentrations of the active molecule without creating substantial systemic levels, which will dramatically lower the risk of adverse effects. Additionally, the potential increased risk of infection and heightened inflammation can be eliminated as there is no need to introduce an additional foreign material to the wound. Natural polymers provide an excellent means of incorporating active pharmaceutical ingredients into suture materials, as the manufacturing conditions are usually mild and do not require excessive temperature, which could potentially deactivate or destabilize the added active pharmaceutical ingredients. Moreover, the controlled degradation of natural polymers can allow for sustained drug delivery through the continual creation of new diffusion pathways as the polymer matrix degrades. Natural polymers also have the unique advantage that they closely resemble the native extracellular matrix, which can permit the effective incorporation of cells and other biological sutures such as plasma proteins and growth factors into suture materials. Natural polymers can therefore lead to new and exciting generation of advanced suture materials with not only improved biocompatibility but also added bioactivity. Yet natural polymers have certain drawbacks that must be weighed against the diverse benefits. Now here we consider the advancements in the field of suture materials by taking a closer look at three profound natural carbohydrate polymers, namely cellulose, chitin and alginate, and how they have been employed to create novel advanced suture materials. The specific properties and unique attributes of these three natural polymers that make them especially suitable for suture applications are being discussed herein. Furthermore, significant breakthroughs pertaining to the use of these polymers in suture material development over the last few years have been discussed. The potential impact and future prospects of these developments are also highlighted. It is intended to open the eyes of material scientists on the hunt for the ideal suture material to the immense potential of natural polymers with their excellent biocompatibility and other intricate qualities to develop advanced suture materials with expert safety and efficacy. Now let's consider the cellulose and its derivatives. Cellulose is the most abundant polymer of natural origin and has enjoyed much attention in the field of biomedical research. So as a biomaterial, cellulose offers numerous advantages such as non-toxicity, high availability, renewability, low cost, biodegradability and other quintessential physical and chemical properties. These properties have led to its widespread use as a biomaterial with applications such as wound dressings, dialysis membranes, controlled drug delivery systems and tissue engineering scaffolds. However, the poor solubility of cellulose in water and other common solvents has prevented its full utilization in the biomedical and related fields. Hence, different derivatives of these promising natural polymers such as oxidized regenerated cellulose, hydroxyethyl cellulose and cellulose nanofibrils have been developed. These derivatives exhibit improved solubility as well as other desirable chemical properties, including the presence of several functional groups that can be readily activated as a result of its key structural role in plant cell walls, and its derivatives also demonstrate notable mechanical strength, making them ideal candidates for new innovative suture materials. Now, natural cellulose fibers have been used in the development of novel suture materials. Then oxidized cellulose have also been used in the development of novel suture materials. Then plant-derived nanocellulose, interestingly, plant-derived nanocellulose have also been used in the development of novel suture materials. Then bacterial derived nanocellulose has also been used in the development of newer types of suture materials. Now let's consider chitin and its derivatives. Chitin is another ubiquitous and useful natural polymer found in the exoskeleton of arthropods such as crabs and shrimps, or in the cell walls of fungi and yeast. Besides conceivable properties such as biocompatibility, compatibility, biodegradability and non-toxicity which stems from its natural origin. Chitin also holds several other useful properties. Now these include a basic nature which stands in stark contrast to the acidic or neutral nature of most natural polymers, as well as a high charge density with the ability to chelate metal ions, high surface area, exceptional porosity and other optical structural characteristics that has ensured its use in a myriad of biomedical applications and makes it a promising futuristic suture material. Chitin is chiefly found in two forms, namely pristine chitin as extracted from crustacean shells and its deacetylated form chitosan, which is an acetylation degree below 50% and higher solubility than chitin. These polymers are naturally broken down in the human body by native enzymes into relatively pure oligosaccharide and glycan moieties. Some of these moieties, such as N-acetylglucosamine, which is the most pertinent component of chitin, is also present in essential human glycoproteins that make up connective tissues like hyaluronic acid and keratin sulfate. This glucosamine is widely used in tissue engineering and wound healing applications for its esteemed ability to regenerate cartilage tissue and facilitate the ordered deposition of collagen. Other moieties such as N-acetylglucosamine, which is released upon depolymerization of chitosan, can initiate fibroblast proliferation and stimulate hyaluronic acid synthesis that will ultimately lead to faster wound healing and less scar formation. Numerous reports have indicated that both chitin and chitosan have accelerating effects on wound healing, making them distinguished materials for wound dressings and suture formulations. Now, accelerated wound healing is, however, only the start of the beneficial properties displayed by chitin and its derivatives. These polymers exhibit a variety of biological functions such as hemostatic, anti-tumor, anti-inflammatory, anti-scarring, antibacterial, antiviral and antifungal activities that can all be used to obtain the ideal suture material. The exact mechanism of action behind the inherent bioactivity of chitin is not yet fully understood, but progress is being made at a staggering rate to better understand this impressive polymer. Despite the limited knowledge on how this polymer functions in vivo, chitin has already moved to the forefront of suture material development, primarily due to the present research studies and developmental efforts focusing on the development of absorbable suture materials with multiple functionalities, including antibacterial hemostatic activities seen with chitin. However, a wide chasm remains in terms of chitin-based fiber formulation with applicable suture properties and functional methods for the production of chitin-based sutures. Still, the immense potential and importance of chitin as an absorbable suture material is evident and can be witnessed in the great number of relevant research papers recently published on the subject. Now, this chitin is used as a potential biomaterial for surgical suture material applications. Moreover, due to the chitin constituents of the suture material, the inventors suggest that properties such as an enhanced wound healing and hemostatic effect can be expected in addition to excellent biocompatibility in the newly invented suture material. Yet, the study that mostly expertly portrays the benefits of employing chitin as a suture material was undoubtedly published by Shao et al., who developed a novel monocomponent multifilament diacetyl chitin suture for the treatment of superficial skin wounds. To assess the feasibility of the produced sutures, an extensive in vivo trial was conducted by employing a full thickness wound model with the popular and widely used Vicryl plus sutures as control. The sutures had comparable mechanical properties to that of the synthetic suture, which meets the standard suture strength requirements and managed to maintain a staggering 63% of its original strength in 14 days post-implantation. Particularly good handling properties with ease of knot tying was noted for the sutures and ascribed to the excellent pliability and modest swelling property of the material. The histological evaluation revealed that the expected pronounced observable sutures with improved bioavailability, while the suture elicited to remarkable tissue response. Chitosan from chitin is used as a potential biomaterial for surgical suture applications. Now, let's consider alginate and its derivatives. The third natural polymer that stands out as a viable option for the fabrication of novel suture materials with expert biocompatibility and potential bioactivity is alginate. Marine brown algae are the main source of alginate, which is a linear polysaccharide consisting of two different monomeric units, namely beta manuric acid and alpha L glucuronic acid, The composition and sequence of M and G blocks in alginate depend on the growth conditions and type of seaweed that the polymer was derived from. This M by G ratio has a profound influence on the chemical and physical behavior of alginate and creates a unique avenue for manipulating certain properties such as the stiffness and swelling capacity. To date, alginate has been investigated